About our first guest.
Eric, I'd love to. We got two very special people here on Controltrends this week. We have Ecorhythm's Vice President of Sales and Marketing, John D. Morris. We also have Dr. Igor Mezic, who is a professor of mechanical engineering and director of the Center for Energy at UCSB, California. Two very, very special guests. Welcome to the show, guys.
Hey, welcome, guys.
Greetings from beautiful Santa Barbara, California.
Well, awesome. Well, guys, tell us a bit about what Ecorhythm does and what you guys are all about, please.
So essentially what we've done is using Igor's software algorithms that were developed at the UC Santa Barbara, we've created what we call the True Analytics Software Platform, which essentially can analyze anything in the Internet of Things where we've got appropriate data available. We're currently focusing on the building HVAC market, but we'll move beyond that once we skin this market. We have a chance to move on to other things. It's a pure SaaS model. It's very highly accurate. We've had a major IT company take a look at the findings we've done in one of their buildings, and there's nothing like this in the market anywhere in the world.
Well, John, let me, I do want to get a little bit more on Igor. Igor, you're a professor of mechanical engineering and mathematics at UC Santa Barbara. Can you tell us a little bit more about your background so we can get kind of immersed in how you came up with this amazing algorithm?
Sure. I'm a mechanical engineer by training. I did my undergrad in Croatia at the northwest side. And I watched a number of people that are close to me, like my dad, who's the captain of massive French cargo ships, and then my father-in-law who started an HVAC company, and he designed HVAC systems for resorts and hotels. I helped him in that, and I sailed with my dad, and I just watched these people do what they do, dealing with also an immense amount of data, but then making very good decisions out of those. And I thought, as I was going on with my professional work, wouldn't it be nice to develop platforms that can help people like that, make those decisions even faster, but equally accurate. And so when I first came to the United States, my graduate work was at Caltech in mechanical engineering, and then I got interested in algorithmic aspects of engineering, and so I decided to do my postdoctoral research in mathematics, and I went back to the United Kingdom, to University of Warwick, and then had a number of offers from the U.S. for professorships. I joined the faculty at UC Santa Barbara, and what was interesting and really great is UC Santa Barbara has a great sustainability record. It has a great group of people that care about environment and energy, and we started an Institute for Energy Efficiency.
Awesome.
It worked out really nicely. Last year we got Shuji Nakamura, my colleague, got the Nobel Prize in LEDs, if you've probably heard about it.
All right, John, you've been around the industry, the building and controls industry, for a couple of decades now. Got great experience. What makes Ecorhythm a game changer in your view?
Well, I've been in this space for about 20 years, going back to the very first networking platform, which was the Lawnworks platform with Echelon. It was effectively a prototype of the Internet of Things. It was not IP, obviously, but once the devices became networked, big data became a real possibility. When I first saw Ecorhythm's technology, it was very clear that they were in uncharted waters, making sense of the data that building systems were capable of delivering.
What are the big problems that you guys are solving, and how does that sort of translate to customers, if you will?
So from a technical standpoint, there are two essential things here, and one is scalability. You really want to be able to scale quickly to a large number of buildings, and the other one is the specificity. And these two things kind of go head to head sometimes, because if you want scalability, you're talking about maybe smaller number of points. You're talking specificity, you're talking about a large number of points. So the analysis of buildings is relatively tough. Pre-commissioning takes months and months of study. What we developed is a platform technically that can, at the same time, take a very, very large number of points, but it's quite scalable. And it gives very specific knowledge to the building engineer that they can utilize and go and apply and correct whatever the machine learning algorithms came up with.
Awesome. John, you mentioned a couple of things here too that I wanted to catch on to or bring to bear. You branded this software, Echo software platform, True Analytics, meaning that this is really what analytics are all about. And some of the other people saying about analytics are really not essentially analytics. Could you tell us about that?
Yeah. So in a real analytics platform, what you're doing is you're taking in the data and then you're coming up with conclusions that are not necessarily just a sensor's out of range. We're looking for what Igor describes as unhealthy behavior based on departures from the normal ebb and flow of energy in the building. I'm going to throw it to you and let you finish this one off.
So there is the ability to go very, very deep and understand, or the machine itself is able to understand what the root cause of a problem is based on a pattern recognition that it does on the various cycles that are occurring in the building. I mean, to just describe this very, very briefly, let's say over 24 hours, a very, very simple problem. Over 24 hours, you have a variety of cycles. Things come on, things come off. Some of them are very healthy. If things get shut down at 6 o'clock in the afternoon, that's a healthy part of the 24-hour cycle. But if you have stuff cycling at 30 minutes on top of that 24-hour cycle, then that might be unhealthy. And so we actually take that information and put it into a sort of a work ticket, so saying this particular piece of equipment is doing that, and this is the root cause, and it might even fatigue and fail because of this. So it's pretty comprehensive, pretty specific. Maybe you want to say how it translates to customers.
Sure. I mean, so when we engage a customer, the discussion always seems to start out with, how can you save me energy? Because the brokers and folks are looking for buildings that are above an Energy Star score or a LEED score above X. And that's a great place to start. Once we get in the building, we're a pure SaaS model. So we generate a great ROI just on the energy alone. But because of our comfort console and the way we are able to demonstrate how a building is performing as a quality asset, where tenants, you can show them you are comfortable in your space, and you can show future tenants that are being brought in by a broker that your building is demonstrably comfortable. That's the second layer of the onion. The third layer is when the engineering staff stops chasing shadows around the building and really gets to root causes, as Igor just explained. You get a much, much more efficient engineering operation in the building, which then adds the ROI. So it's three layers of things. And if you think about the actual energy piece of this deal, it's a small slice of a very large rent roll.
Yeah, it seems like, the operational cost is a huge piece, but if I'm understanding you guys correctly, because, there are a lot of, really nice analytics packages in our industry already. It sounds like what you guys do, maybe that's a little bit different, is not only do you do the analytics, but it seems like you guys have modules that do the diagnostics too. So instead of relying on somebody to interpret that data, you guys, your algorithms would interpret it and identify, like Igor, you said, root causes and things like that?
Yeah, and this is semantics. It's great to point out that difference, right? Diagnostics versus analytics. We call it true analytics because it goes deeper than the usual. Let's make a correlation between the outside temperature and the amount of energy that the building should be using. We're going to go specific to a VAV or to an air handling unit and diagnose what is wrong with that type of unit, and then that leads to predictive maintenance aspects of it. It leads to ability to improve the comfort, and it kind of pays for itself by the fact that it actually has substantial energy savings associated.
Yeah, absolutely, fellas. And I think the thing, some of these packages, and it sounds like you guys probably already do this. If not, would be very easy to do. But as you guys know, when you get a building, somebody comes in and tweaks everything, they commission it, and probably 10 minutes after they've got it set up working perfectly, it comes out of commission. So one of the trends that Kenny and I have been tracking, and it seems like companies like yours are really leading that way, is what we call a buzzword is constant recommissioning or automatic recommissioning. So you, for example, are looking at a PID loop, a proportional integral derivative loop, and all of a sudden that valve or that air handler now is not controlling the way it was before. So maybe you send a signal to it and it re-auto tunes itself and comes back in. So there's a constant recommissioning of the building, if you will. Is that something that's built into your guys' package already?
Absolutely. I think we're talking about the real-time aspect, and I'll comment on that. I'll comment on that in a second. But the first part that I want to comment on is the idea of constant commissioning in the community, energy and buildings community, has been around for a while. I think what eCoritum solves specifically in that context is the scalability of the idea.
Nice.
Because a great engineer can, of course, do constant commissioning, or a great group of engineers. You can have 100 engineers or 200 or 1,000 engineers working on a problem. They're going to do a great job. There is no doubt about it. The issue here is to help or even do completely automatically in real time that particular job. So to take the domain knowledge, make it into a machine, artificial intelligence platform that really does something. Now, we don't do real time as of now, and the reason for that is that, of course, we also trust the building engineers to pursue their judgment as well. I mean, there is this notion of building whisperer that we talked about in an article a couple of months ago. So when we talk to them, they require us to give them the information, and we trust them to do with the information whatever they need to do with the information at this point in time. There is no technical restriction on the platform to be able to do the writing that you've just alluded to. And I think ultimately that's where we are going to when companies like ours, gather enough fault detection and artificial intelligence capability to basically just run the building on its own. I think that's a beautiful future that enables building engineers to work even more productively. That's what I think.
Yeah, and the other thing that gets addressed by this, of course, is if you're following the conferences and things, one of the alarm bells that is constantly being sounded these days is that the building whisperer as a profession, those people are retiring. And
good point.
People coming behind them are somewhat less skilled. They move around. They don't stay in the same building for 20 or 30 years. This platform makes a junior engineer much, much more efficient and can actually approach what the building whisperer could have done if they were still in the building after those guys head off into the sunset.
John and Igor, this is fabulous stuff because we're very much interested in it. And we think we're there. We think the technology's there. But are there limitations to just how intelligent a building can be? And you mentioned data-ready buildings. What do you mean by that? I mean, does every building has the potential to be a source of great savings? And how do you get to it? And how do you make this more of a commercial approach where people like us can sell it?
So basically, any BMS system is generating data. Sensors are measuring things, actuators are moving, positions are available. The trick is to be able to get the data out of the building. And we've been able to pretty successfully figure that out. It's taken some time, and there are companies that are being tasked by their investors to actually go solve that problem. I just came from AHR Expo last week, and we identified 3 or 4 platforms that are aimed specifically at conditioning buildings that aren't necessarily data ready at the level that we like. I mean, we'd like a 5-minute trend if that's capable in the system. We found these appliances that can artfully work within the technical constraints of these older buildings to be able to get the data out. And that expands our market share dramatically as we're able to move farther and farther back in the history of building controls to be able to make more and more of them data ready. But that's one of
John,
the key
as a corollary question, I mean, so when you were talking about layers and stuff, so how, and data ready points, so basically you're working right off the infrastructure that's already in place, whether it's a DDC system or a building automation system. You're agnostic. You can take anybody's information and apply your technologies to anybody's stuff. Is that correct?
Yeah, that's the value of a pure physics approach. And Igor can speak to that directly.
So we certainly need data, but as you said, we're agnostic to where the data comes from. To just give you an example, we take like between 1,000 and 15,000 data points on 5 to 15-minute intervals, and we need to get the data from somewhere. As John alluded to earlier, we can ramp up a building if it's data ready in hours to a day. So it's very, very quick. I think that trend is going to continue. More and more buildings are going to be becoming data ready. We initially focused on large commercial buildings because that actually makes sense for a number of different reasons. They spend the most energy and they're most data ready.
Yeah, and to jump off of that a little bit, one of the differentiators, and Igor just swerved into it with our platform, is that we can bring up a building in hours to a day or two, as opposed to the rules-based system that requires you to go in and actually know about the sequence of operations and all the different things that are going on in the BMS system. We hear stories of installations taking weeks to months. I'm aware of one platform that the entry price is somewhere in the six figures. That platform's now out of the market. We're able to do this with essentially no upfront cost to the building owners, except just getting the data out of the building. So we can execute a pure SaaS model that other platforms just simply can't do.
So listen, I'm fascinated by this, and I'm thinking about it, guys. So I'm wondering, is there an add-on module that will look at the stock market? So while it's tweaking my building and give me information on my building, it's also tell me which trades I need to be in and out of.
That's a great question. Any company that's trying to do things that are new and within the analytics context needs to understand what their domain knowledge at a particular point in time is. And Ecorythm is certainly looking at the more general Internet of Things setup, things like wind turbines, automotive, other things. Stock market, maybe.
That's next. It's on the drawing board.
Well, no, but you sort of bring up a good point, and I'm fascinated by this too, because when Ken Sinclair turned us on to you guys, he was talking about you guys were using artificial intelligence, which to me applies that it's sort of the algorithm sort of self-learning in a way, which obviously there's one layer of it where they take the data and they make certain assumptions, but over time, do your algorithms get smarter?
Yeah, so that's actually an interesting point. So and that comes from the research we've done earlier. We actually tune these things so that they have a time dimension. There is one big difference between the algorithms that are used here and the algorithms that typically get used. You typically get correlation-based algorithms that say, like I said before, if this is out of range, then go and look at some other thing. Here we are actually taking a look at the time dimension. So how do things change over time? And even the companies that do artificial intelligence today, there are very few, I frankly don't know of any right now, that are doing the time dimension the way Ecorythm pursues it, coming from some earlier, DARPA-based research that we've done. So the time dimension is very, very important to this technology and to those algorithms, and the software learns as it goes.
Well, speak about that, because you really tweak something when you start thinking about time. I can think of things like when you change your filters and all are obviously time-based events as well as usage-based events. But speak more about how you guys, because I definitely get that it's important, but could you speak more about where you guys see that how would that show up in somebody's building? I'm a building owner, or Kenny and I are out trying to sell your system, and we go, the stock market module's not quite out yet, but we're bringing time in on this, and this is going to save you because there's the time dimension that allows the algorithm to become more learning, if you will.
So if you take a look at, for example, the typical issue of high frequency cycling,
yep.
On the VAV side, that's something that's very, very difficult to detect with static-based algorithms. I mean, what do you really detect? You're detecting a cycle.
Right.
So here's a time dimension that absolutely necessarily needs to be in there. If you're talking about the behavior of the building over a year, and correlating that with energy, then you're taking a snapshot over a year. We take a 5-minute one, right?
Yeah.
So we see the cycling in the VAVs. To just give you an example, on a piece of work that Igor has done, there was an issue in which a lot of heat pumps, a very large percentage, 20 to 30% of heat pumps, were cycling at very high frequency. That leads to fatigue. That leads to obviously possibly smoke coming out of those compressors at some point in time. So being predictive about it, but taking into account the time dimension, so not just the mean. Because the thing is cycling around the mean, right? If you just take the mean out and you're not paying attention to the fact that it's cycling, you have lost a piece of information that possibly leads to energy waste and a lack of predictive maintenance.
Well, Igor, the piece I heard that, and correct me if I'm wrong, but it seems like by adding the time dimension and an infinite time dimension as opposed to a finite time dimension, it seems like your predictability is going to go way up in accuracy.
It goes up in accuracy. I do have to say, we do have the temporal, so time dimension and spatial dimension as well. We pay attention to system as a whole, rather than just the time dimension, right? So it goes up with both the number of points, spatial number of points that are accessed, and the resolution in time. When you combine these things together and you have a chain, let's say you're detecting the same time signature in your chiller. Let's say the chiller is oscillating at a 30-minute time scale, and in an AHU and the VAV. Where is the culprit in that chain? I can tell you, for example, that a system might come up with a statement that says it's a high gain controller from the zone to the VAV that's actually causing the whole thing and causing the oscillation. Everything in the back is reacting to that. Or, no, it's the chiller. Actually, we had a situation in which the chiller can spend not at those time scales, but let's say 2 to 3 hours. These things are highly correlated, and you need to take a look at the variety of time scales in the system and what the connections between the different parts of the system are. So we don't look at an isolated component like a VAV just by itself, or rather the software doesn't look at an isolated component like a VAV by itself. It actually looks at a whole chain that leads to something in that chain being wrong and then pinpoints that. And so you can see how the spatial and temporal could play a pretty substantial role.
Well, it's like the difference between a 2-dimension image and a 3-dimension image, right? I mean, you're adding another dimension to it that, cool. This is great stuff.
Well, Igor, what happens next? In other words, it sounds like you guys got a really good start and you really got a very, very interesting, game-changing, technically sound, scientific approach. Where does Ecorhythm go from here? How do you, what's the future hold as far as like, how are you going to commercialize this, if that's the right word?
Well, so, we're starting with HVAC in buildings. That's just the beginning. It's the first IoT application that we've applied the technology to. But as Igor can tell you, when you move out into smart grid, smart cities, automotive, any number of different IoT applications where the same kinds of physical events are taking place, any of those things this set of algorithms can be applied to, as long as there's a little domain knowledge that comes along with it. And I'll throw that back to you, Igor. You can expound.
Yeah, we built the software platform to be layered. in the sense that it takes the physical data, it recognizes the patterns, but then it has the layers of abstraction that can handle a large variety of diagnostic goals. So if you give us a wind turbine or a car engine, we do have a platform that is a physics agnostic platform, and then we have a part that is physics recognizing. Let's split it in those two ways. And those two things are modular in the sense that whatever is recognizing the cycles has the domain knowledge in it. A car engine or a wind turbine is actually going to have a 24-hour cycle, but the car engine, not necessarily. It's going to have very, very different patterns in it, right? So that's the part that needs to be domain conscious. The part that is not domain conscious and that is universal and it's organized as in software layers is really the part that our great software team has built in. So that enables the universality. We don't need to go in and really change our software platform in order to tackle a new Internet of Things domain.
Well, Eric, I just want to throw this. I've been waiting to say this. Dr. Mezic is also an expert in complex dynamical systems, both as a member of the Center for Controls, Dynamic Systems Computations, California Nanosystems Institute. But his major scientific contribution in the field has been the development of operator theoretic methods for analysis of complex dynamical systems that led to a massive number of applications in the big data dynamics, a term that Dr. Mezic coined. So we're talking with one of the top sharpest.
Talking to the father of the guy who called it big data, huh?
So Kate, we welcome.
That's awesome.
Space to reduce our carbon footprint. We need to become more energy efficient and save more money in operation technology. And it sounds like you have the dynamic, you have the future in your hands. And when you go public, let us know.
That'll be really nice. But thank you. This was very pleasant. I should say I only added big data dynamics to it. Dynamics is very important to us, as I mentioned. But thanks for having us.
Well, that is definitely the most important D in big data, dynamics. The dynamics, anybody can do big data, but big data dynamics is you guys. How do people get a hold of you fellas who want more information? Website?
Yeah, www.ecorhythm.com. That's ECORITHM.com.
Listen, guys, we look forward to keeping track on you guys, and hopefully you will see a meteoric rise for you guys. And anything we do to help, let us know. We'd love to have you come back on Control Trends, sort of keep us updated from time to time.
We'll join you anytime you ask.
Thanks, fellas.